I have a lot of interaction with my audience, which is the solar industry globally now. So thank you to Chile for adding that. And I live off grid. That's a picture you just saw of my property in near Melbourne, about an hour and a quarter out of Melbourne. These are some of the people I live with. We've lived off grid for over 45 years, and it works. It's a lovely place to live. So hang on, just switching over to the next one. There we go. Australia and solar. It's apparently the highest per capita in the world uptake of solar. So currently we've got 2.3 gigawatts of rooftop solar and another 10 gigawatts of large-scale solar. So it's you're very, very popular. It's almost 1 in 4 homes have solar on them now. So it's a very ordinary thing to see. What that has created is some issues associated with connection to the grid. So grid voltages are starting to rise, particularly in the middle of the day, and causing some disturbance. Also causing, oops, sorry, I turned it off. Causing the network to want to ramp down the amount of solar generation. So it is a bit of an issue at the moment. Adding batteries to it has meant that people are now more autonomous in terms of their energy, so they can use their solar at nighttime because there's not very good incentives to export surplus solar to the grid. So we're seeing people wanting to basically use their own solar energy directly during the day by scheduling appliances to come on when the sun shines, or using battery storage to shift that energy that you've stored so you can use it in the evening. There's a breakdown by state. The sunnier states like Queensland, etc., are very, very strong growth in solar. One of the things that's worth noting is the amount of jobs that solar creates. It's a very big employer. Unlike mining, which Australia is quite famous for, mining's actually, in terms of dollars earned, is a very small employer because it's generally uses large machinery to do a lot of work very quickly, whereas solar is much more hands-on. There's a lot of labourers, electricians, technical designers, salespeople, so it's a really big employer. And that's a growth showing how solar has taken off from my little floating pictures covering part of it. Hang on, I'll just move myself over here. Yeah, so that's just showing how solar's grown in the last 10 years in terms of the average system size on a home. So 10 years ago, 2010, 1.9 kilowatts was the average size system on a roof, and now it's over 7.5 kilowatts, 7.6 kilowatts or so. So people are putting big systems on now. Now, partly that's skewed because of there is still a market for what they call clean energy certificates. So when you install solar, you get a discount on the price of solar. About a third of the cost of a pure solar system is paid back to you for certificates for the clean energy it produces, and that's an upfront discount. So that's kind of made bigger systems more popular because you get more discount the bigger the system is, and therefore people are really ramping up to the capacity of their roof. And this is just showing the mix of energy on our national grid. And in yellow, you can see solar. And I'll just move myself over the side again. Here we go. You can see down the bottom here is brown coal, then black coal. So this is from like Monday midnight through to the afternoon. That's midday. You can see where the solar's really peaking here in the middle of the screen. We've got quite a lot of wind and hydro, though hydro is not growing, wind is still growing. But the problem is that solar really is not meeting the peak demand of the grid quite perfectly, and therefore sometimes it's too much solar and sometimes it's not enough. So the issue really from network operators is how do you manage intermittent sources to get a reliable supply, and that's the challenge of any energy market is to manage that supply and demand. All right, so let's get into the technical side of stuff, and we're going to talk about what in Australia is known as hybrid systems. Now, I should define my terms. I'm talking about you've got solar panels, you're connected to the grid, and you've got battery storage. So it's hybrid in the sense that it's not really off-grid, not really fully on-grid. It's kind of can do a bit of both. So we're going to look at some of those configurations. Now, first two slides I'm going to show you is just a really simple, and by the way, these slides will be shared with you after the presentation as a PDF, so you're welcome to you don't have to draw down or copy any of this if you don't want to. I'll share them as they are. I've got two screens here showing the many ways that battery storage can be added to a typical grid-connected system. So at the top of the screen there, you'll see M is meter, so that's the grid. INV is the inverter. Load is your home. And PV is solar panels. So that's your typical grid-connected system that the PV system is generating in parallel with your home's loads. And so the loads are consuming the solar energy first, and any excess is flowing to the grid. Then we've got a Powerwall type configuration. Now I call it Powerwall because people are familiar with the brand Tesla, and the Powerwall batteries, very popular. They actually are an inverter and a battery in a box. And so I've put a dotted line around it. If you see, it says PCE, power conditioning equipment. And so we've got a battery in a box, and we may have some PV connected into that system. Next one down is where you've got a integrated storage. So you've got a device that can take solar and battery and inverter all connected together. And down the bottom here, we've now got backup capability. SA loads means standalone. That means even when the grid fails, you still have power on some circuits. Now, that means the top three, if the power goes off, you don't have any power unless you have some capability of supporting standalone loads. I'm going to go into these differences in more detail. This is just a high-level overview first, and then I'll go through each one of them with a bit more interaction. So the all-in-one systems where you have a hybrid inverter with solar panels connected to it, a battery connected to it, and probably a backup circuit, or sometimes called a UPS or EPS circuit. These are just marketing terms: UPS, uninterruptible power supply, or EPS, essential power supply. But effectively it means that when the grid goes off, you still have some power, depending on the capabilities of your hybrid inverter. To run the whole home off that standalone loads is pretty big ask, because generally homes will have peaks of energy greater than the inverter can supply. So more normally the middle option is where that only your essential loads are supplied, or the things that you want to back up if the grid fails. So that's the middle line. And the bottom line is, it's going to require a bit more explanation. There's actually two inverters. There's a battery inverter and a solar inverter, and they work together to supply energy to the loads, even when the grid's down. So going over to my drawings now. Now, these are the same systems that we just looked at, but one by one, and I'm going to spend a bit of time explaining them with some drawings over the top. So I'm just going to switch to that, to my overhead. Okay. Yeah, hopefully you can see me now. There we go. So this system here is a retrofit of batteries. So here we've got an existing solar system. The customer's already got solar installed. They're perfectly happy with it, and they go, oh, how much are batteries? I'd like to add battery storage to it. So this here is a battery storage system with its own inverter. Now you might think of this as, say, a Tesla Powerwall, for instance, would be this kind of system. It allows you to what's called AC couple. Now the word coupling is how is the solar energy transferred to the battery. Well, it doesn't go through, this is the DC cable here, then it goes through an AC cable gets converted back to DC. So the coupling between the solar generation and the storage is through the AC bus. So it's called AC coupling. Now the beauty of AC coupling is it doesn't matter what brand the solar inverter is. or what brand the battery inverter is. They don't actually need to directly communicate with each other for it to work. But what they do need is some way of measuring the flow of energy. And that's what this here is. Now, this is not your utility meter. This is an upstream meter that's usually provided with the AC coupled inverter. So you'll notice I've just done a little Wi-Fi symbol here, but in practice, that'll be a data cable connecting the two together. And so that data cable will allow the battery inverter to see which way energy is flowing. Is it flowing towards the grid like this, or is it flowing from the grid back to the loads? Now, if it can see energy flowing out, it communicates that along this data cable, and so the battery inverter suddenly sees as an opportunity to capture surplus solar energy. So let's say it's the middle of the day, and this inverter is putting out 4 kilowatts of AC power. The loads are consuming 1 kilowatt of AC power, so 4 kilowatts this way, 1 kilowatts to your home. That means we're going to have the difference of 3 kilowatts flowing out to the grid. And so there's an opportunity to capture that. Now, this doesn't happen instantaneously. Generally, there's a ramp up 10 to 30 seconds or so where the battery inverter sees that surplus opportunity and starts to charge its battery up to 3 kilowatts. So what it'll do is it'll reverse that, so the extra 3 kilowatts is going into the battery system here and charging until the battery is full. So that's the charge process. The reverse is, and typically at night time or whenever there's a mismatch between solar generation and what the loads are consuming, it will reverse that process. It will, for instance, see that we're no longer exporting energy. We actually start to consume it. So energy's starting to go this way. So we're seeing 2 kilowatts of consumption. So at this point, it knows that, so we've got 2 kilowatts of consumption here. It's going to start exporting 2 kilowatts. So the solar's gone off because it's nighttime. So there's 0 kilowatts from the solar. And so now we've got 2 kilowatts coming from the battery, and it's going the other way. And so it's offsetting this energy that would have been drawn from the grid by reversing that direction of flow. So that's really all done just with software. The ability to measure energy at this point here allows the brain, which is the AC coupled battery inverter system, to manage the flows of energy with installation. So that's the basics of a simple AC coupled system. Now let's go to the next slide. Now I call this AC coupled number 2. Now this is not a very common configuration, I should say, but it's where you have you have 2 inverters like in the previous picture, but now the battery inverter has 2 AC ports. It's got a grid side, so grid side, and it's got a load side. So it's not just a single port AC battery inverter. It's got two dedicated ports, and it's got the ability to receive energy or export energy on its load side. So it's not just an inverter that outputs power, it can receive power from another source, in this case the solar inverter. Now we've put the load center in the middle here. Load center is like your switchboard, all of your home essential loads. And the advantage of this configuration compared to the other one that I just drew is that if the grid fails, we still have power. So if the grid goes off here, we still have power because the battery inverter becomes what's known as a grid-forming inverter. It actually creates a stable voltage and frequency to which the solar inverter can synchronize with, and therefore everything keeps on working. So this kind of configuration allows you to have not just backup, but also backup with solar charge, even when the grid's not there. So you don't lose your solar. That's one of the big advantages. I should point out that I'm happy to take questions throughout the session. So David's going to filter some of the questions and pass them back to me. So please feel free to just type them into the chat window so David can view them. So here we've got a DC coupled system. Now remember I said coupling is how does the solar energy get to the battery, and in this case it's going from the solar panel, which is DC, orange line, to the battery, DC. So it's going internally through that unit. It's not getting converted to AC to charge the battery. So the advantage with a DC coupled system is it doesn't actually need the grid to charge the battery. So you'll still be able to charge the battery without the grid. It's very efficient because you haven't got an extra level of conversion. And it's also all in one. So this system here is both a solar inverter and a battery inverter all in the one system. So simplicity of installation. It still needs this upstream energy meter though to be able to support the loads or to charge its battery from another source, from the AC side. So it is possible with this system still to charge the battery with AC, which would be grid power. Why would you want to do that? Well, you might actually have variable pricing on your grid power. You might have times of the day when it's very cheap, and that might typically in the middle of the night when you're not using any power. So you might want to charge a certain amount of your battery with cheap grid power, as well as using solar during the day to charge it. So that's one of the other advantages of this configuration. But this meter also is, just as in the previous diagram, measuring which way the energy is flowing. Is it flowing that way or this way? And therefore communicating, like I say, usually with a data cable to the hybrid inverter and telling it what to do, telling it whether to charge or discharge its battery to support the loads, to offset any grid power that might be imported. But of course, you can do almost anything you like. There may be an incentive to export energy. This is becoming a bit of a market in Australia, which is where when the grid needs power, getting people who've got small systems all at the same time to export their power back to the grid and at a higher rate. It's a sort of spot market rate. And currently that's a 30-minute spot market. It's going to be moving to a 5-minute spot market. So people can actually export small amounts of energy, but it's usually managed through an electricity retailer, and they aggregate or collectively do it with all their customers who have battery storage. So that system means that all those little batteries effectively are one big battery on the grid and can provide grid services. So how are we going, David? We got any questions yet?
No questions so far, Glenn. It seems they are very captured by your drawings.
Okay, all right. So this is a slightly different version. Now, actually, I'll bring that drawing back again. You'll notice that this one here shows we only have a single connection to a load center. And what will happen is if the grid fails here, we actually have to turn off that inverter. It can't support the loads when the grid fails. So in this design, there is no backup power available. But there is a way to make that work as a backup system. And that's what I've got here. Now you might notice it's almost the same diagram except for this device here, which the acronym ATS is used, referred to as an automatic transfer switch, which means that it's powered by the grid. So when the grid fails, if the grid fails over here, this switch automatically isolates this connection and connects through this connection. So it allows this inverter to carry on powering a backup circuit safely without risking trying to energize the grid when the grid shouldn't be energized. Now, the reason for that is that the grid goes off for lots of reasons, and one of them could be, there's been a storm and power lines have fallen down, and you don't want to start exporting power out to the street when the power lines are lying on the ground. So it's a safety issue. So this achieves that safety by isolating at the connection to the load center, but then you've got a separate backup circuit. Now this could be a single power outlet, it could be a switchboard, or it could be some dedicated circuits inside the switchboard. So I've shown it here as a dedicated a dedicated switchboard, but it doesn't have to be. All right, and once again, that meter plays that important role of seeing where the energy is flowing when the grid's available and whether it's going to support the loads with battery power and solar power as well. One more, and I think this is, I've got two more. So this one's very similar. So just to flash them back again, this one here, I've got an ATS. So that means I've only got one port on this inverter, one AC port, and it can actually change its mode of operation from grid feeding to standalone. And it does that change of mode whenever the grid's lost and this automatic transfer switch operates. That does mean, though, you will have a loss of power for typically 10 seconds or more when that occurs. So if the grid goes off, the power goes off completely to the home, then 10 seconds later, the backup circuit comes on and you've got backup power. So it's not uninterruptible. But it is possible to have virtually uninterruptible. Now, I've got to be careful here. A true UPS system has no break, but these systems have to have a switched break, but it's done very quickly, often 10 milliseconds. So if the grid fails, this circuit here will have typically a half cycle interruption and then carry on working in standalone mode. And so the advantage there is almost no loss of power. Now, for many appliances like lights, even computers, often they won't even notice that half a cycle loss of power, but some sensitive equipment may reboot. So you can't call it a true UPS system, but it also means it's much simpler to install. That little box that I called the ATS is often for an electrician another hour's work of screwing to the wall and connecting it up and programming the inverter to use it, etc. Whereas inverters that have a built-in transfer function internally and two ports, they have a grid port and a backup port, are much quicker and easier to install. So that is another option. Okay, so now the last one, it's a little bit fun. I jokingly refer to this in Australia as the death spiral accelerator. Now, if you wonder what I'm talking about, there's been terms used that solar and batteries will be the death spiral of the electricity grid because it's reducing demand on the electricity grid, and the way that the grid's been funded has been through consumption. The more energy you use, the more you pay, and they use that income to pay for upgrades to the grid. But people are choosing to use less and less grid power, so they're having to find ways of maintaining that investment in their infrastructure. And one unfortunate way is just to increase the price of electricity. So in Australia, we've seen some very big price rises over the last 10 years, and so doubling of electricity prices on the grid, which means more people start to use less grid power because the price is high. They put in solar, even without batteries, and they use less. So you can see there's a spiral there. The electricity retailers raise the price because people aren't using enough, and so people start using even less, and so they raise the price. So that's called the death spiral. Now, I jokingly refer to this as the accelerator because one of the impediments to using more solar is the limits that you are given on how much solar you can connect in parallel with the grid. Because when you parallel a generation system with the utility grid, you're interacting with their network and therefore having impacts on its operation. And they're perfectly within their rights to limit how much impact you can have. And that's generally just done by inverter sizing in Australia. So here, in most jurisdictions, a single-phase home can only have a 5 kilowatt inverter, sometimes 10 kilowatts, but can't export more than 5. That's for a single phase. That means that I pointed out customers are getting bigger and bigger systems. So, 7.5 kilowatts is the average size system now. And a lot of people, particularly in rural areas who are on weak parts of the grid, are told they can't even have 3 kilowatts of solar. That it's too big. So we're seeing people looking at alternatives, and this one here is where they've got an inverter that doesn't parallel with the grid. They have batteries and they have solar, but what they've got between the grid and their batteries is just a rectifier, a battery charger. So as far as the utility is concerned, the customer has installed a battery charger. There is no reverse flow of power. There's no paralleling with the inverter, with the grid, so it can't affect its safety or operation. And therefore, in Australia, there's no utility limits on this. They can't tell you you can't install it. It's really like you don't have to get permission to install an air conditioner. Well, you wouldn't need permission to install this system because it's just a rectifier. But what it means is this home is becoming more and more off-grid. So everything on this side of the picture is effectively an off-grid system, and the only thing the grid's being used for is just backup charging whenever the solar and battery isn't enough. So I call it the death spiral accelerator because it's making it easier and easier for people to use less and less grid power. So anyway, that's just a little bit of a quirky characteristic of maybe Australia because of the limitations that we have. So that's I'll just cut back to me. Okay. All right, so hopefully we've got a few questions at this point.
Yes. We have one from Christian, and he's having a question for the AC coupled number 2. And he's asking if the inverter that they're using in that case needs a special certification in Australia.
Okay, AC coupled number 2. Yeah, right. So actually I've got that as a slide, so let me just bring that up as a slide. AC coupled number 1, AC coupled number 2. Here we go. So that one there. It doesn't actually need any different certification. So this inverter here, I'm calling it a battery inverter because it's got what we call a grid port. That means it can parallel with the grid on the left-hand side of the picture. Because it can parallel with the grid, it needs to have a certification of permission to connect to the grid. We have a standard for inverters that connect to the grid, which is a AS4777.2, and that's a safety and performance standard for any inverter that parallels with the grid. So this battery inverter meets the same requirements on the grid port as is required for any solar inverter because it's interacting with the grid. But on this side, it's effectively a standalone inverter. It produces power whenever the grid's not available. And internally, I can't draw on my screen at the moment because I haven't got my pencil on. Internally, the power can pass straight through as well. So it can pass energy through from the grid to the right-hand side and parallel with it at the same time. So it can use grid plus battery to supply loads.
Okay, so basically there's no separation and certification if you're using a solar inverter, battery inverter, simply that you have something connected in parallel to the grid and that needs to comply with these technical certification. Okay, that's interesting.
I should add that you can't just assume that all battery inverters can do this. It's a special requirement, and they do have to get a certification, the same as solar inverters.
Okay, great. Well, Christian has another question. I'm not sure if I get it right, but I will just try to let out all my technical knowledge. He's asking about the death spiral scheme. Accelerator, that was it. If there's any technical condition that needs to apply for a rectifier in that scheme. No, it was the last one. It's the same one? Oh, yeah.
It's a different drawing, but it's the same concept.
Same concept.
Well, not really, other than as it's effectively an appliance connected to the grid. So the battery charger, I pointed here, I've called it charging only. It means that you're just connecting an appliance that can utilize grid power only as a load. So there's no extra technical requirement. I should point out that there's products available that do this that are very, very cheap. Just thinking of a brand name, MPP Solar, make one. And in Australia, they sell for about $900 Australian. It's a 5 kilowatt inverter that can take about 7 kilowatts of solar on it, 48 volt battery, and it's very cheap. but it needs no certification to connect as an appliance to the grid because it's only a load. It's only a battery charger.
Okay, good. Understand. Okay, there's another question from Pablo, and he's asking the schemes that you showed us, is it only for low voltage or also medium voltage system?
Only for low voltage, because I presume you mean 230 volt or three-phase 400 volt systems. They're low voltage in Australia, and that's the only type of supply you can have to a home. Medium voltage would be, in your thousands of volts, would be supply for transmission.
Yes, yeah, I suppose the same. Okay, that was everything, I guess.
Cool. All right. Well, I'll keep going. I've got a few more slides here. So I just wanted to talk a bit about, in terms of design of a hybrid system, things that you need to consider. So what this picture is showing here is that there is the blue area is loads energy consumed, so energy that's going to the loads. The yellow area. Yep.
I will just interrupt you because I think I got the wrong question. I think he was Christian was helping me. I think he was asking about if for these high voltage batteries or low voltage batteries. I guess that was the question.
Oh, I understand. Oh, totally. It works with any voltage battery. So what we've seen is that traditionally inverters ran on what we previously called extra low voltage, so 12, 24, 48 volt. Yes. But the move towards high voltage batteries, particularly for hybrid, is really the trend now. And the reason for that is at around about, for single phase inverter, around about 380 volts or so is the sweet spot for the inverter efficiency. So you're not having to go through a low frequency transformer to step the voltage up from 48 volts to 400 volts internally, and therefore the battery, the high voltage battery, is connecting directly onto the DC bus of the inverter at high efficiency, and it also means the cable sizes are very small and your losses are very small. So instead of putting in 50, 70 mil cable, you're putting in 6 mil cable. So everything's cheaper to install, more efficient, and the inverters are much, much cheaper because they don't have a large toroidal transformer inside them. They're transformer-less.
Okay, yes, great, thanks.
Okay, so back to this. So this is just showing the mix of energy over a 24-hour period in a typical home. And what I wanted to point out is that the energy coming from the battery is being capped at 3 kilowatts. And the reason for that is the size of the battery inverter. So just adding a battery system or AC coupled battery system to a installation doesn't mean that you will offset all of the customer's load energy, because the rate that it can deliver it at is limited by the inverter power of the battery inverter. So this inverter at 3 kilowatts can no longer supply all of that power consumed in the evening, and therefore there's still grid power coming in. It's not wrong, it doesn't break it or anything, it's just that is a limitation. So as a designer, if the brief is we don't want to use any grid power, we want to have a big enough solar and battery system to hardly use any grid power at all, you'd have to size the battery inverter for the maximum demand of the home or installation. You have to think what the peaks are going to be. The other thing to consider from a design point of view is the storage capacity of the battery system. Now here we've got a battery system charging in red, that's the state of charge. So it's empty in the morning, it's charging up during the day from the yellow, the solar. It's reaching 100% charge at about 1 o'clock, and then it's flat topped, which means at that point it's no longer charging and the surplus power is spilling to the grid. Now, there's nothing wrong with that, it's perfectly safe, it works, but it is a lost opportunity if grid power is exporting it is not, and there's no financial incentive to do it. So you may need to consider sizing of the capacity of the battery to meet the generation capability of your solar and also the consumption of energy of the loads. Now that's actually another whole webinar that I do. In fact, I'm doing it for today for Engineers Australia, is how to size the solar and battery system. And this last slide is actually monitoring energy on my home. And the reason I've thrown it up here is often you see pictures like the previous slide, so I'll just go back to the previous slide, where people draw nice, smooth, rough, lines of energy increasing and decreasing. And often that's really a network view of energy on a network when there's hundreds or thousands of customers. But when you look at one customer, the one that you're building a system for, the energy looks more like this. So this is my home. I've got 3-phase power, and you can see the red is got little steps in it. That's the fridge turning on and off all night long. And then the coffee machine comes on at 5 a.m. There's a big spike, and then it cycles off because the water's got up to temperature. So what you're seeing there is very spiky loads, and the green is solar power, so it's not a very good day. It's a cloudy day with scattered clouds coming and going. So actually getting a good match between consumption and generation isn't simple. But when you add batteries to a system, it takes away that mismatch, because the batteries can jump in and supply those peaks. And whenever the solar disappears, it can also supply those peaks. Or in reverse, it can charge the battery when there's excessive solar when compared to the customer loads. So that spiky nature of a single residence is the challenge, and batteries certainly help with meeting that challenge. Now, I've come to the end of my discussion around batteries on grid. I've got a couple of extra slides, if you like, which I'm just talking about solar panel optimizers, because I didn't get to this, I think, in the last presentation. So the advantage of solar panel optimizers, or what technically called module level power electronics, MLPE. Module level power electronics is where the solar panel itself has some device attached to it that manages its generation at a panel level, not a single inverter down at the switchboard, but each panel has a management device. Now that can be done with DC or AC. So these are DC management devices, sometimes called optimizers, brands like Solar Edge, Antego, Huawei. They all make these DC optimizers. And it means every panel works independently of every other panel to its best of its ability. So it's great for shaded sites. We've got some shade on some panels and sun on others. Engineers love it because they can monitor every panel. So it's great for seeing the performance of a system at a granular level. And it also can add safety, because in a DC string, you often, certainly in 3-phase, you're in 800 or 900 volts. So you've got very high DC voltages on the roof of a commercial building. But when you have optimizers, the highest DC voltage that's not managed safely is one panel. The string, even though it might still be in hundreds of volts, is dependent on those optimizers sensing that they're safe to operate. So for instance, if there's a fault, the whole thing shuts down automatically and you've got no high DC voltages anywhere. So safety is a big plus. What does it look like? Well, this is actually my neighbour's house. We'll put a system on there just to show how this is a Solar Edge system. That panel number 1.1.4 is actually just in the shade of the second story of the building, so its production is less, therefore it's darker in this representation. Now normally that would be a problem in a string system, have one panel that's always got a bit of shade on it, or mostly in the morning it has shade on it. But it doesn't matter when you have optimizers, because it's effectively just a weak generator, but it's not a weak link in the chain. It's contributing as best it can. The other type of module level power electronics is microinverters, and here's a few pictures of microinverters, similar size to optimizers, about 100 mil square roughly. There's been a big shakeout in the microinverter market. A lot of products left the market because of reliability problems, and so there's only a few left standing, and you could say the good guys are the ones left standing, because it's very challenging actually to put an inverter in a box on the roof under a panel, and so to deal with the environmental challenges of that is no trivial matter. But they do work. I think SMA kept on promoting they were going to make one, but they never did, so the SMA one never happened. But Enphase has certainly been around for quite a long time, and there's a couple others there. So that's microinverters and their ability to manage at a module level the same benefits of safety. You've got low DC voltages, you've got monitoring of every panel, and you've got tolerance of shade. Okay, well, I think I've come to the end of my presentation. I do actually have some more stuff which will go out with this, but I'm not going to present it now. I call it the 7 deadly myths. There's always a hook for the next thing. But just before I kind of wind up, I did want to just give you some other avenues for learning stuff that I do. I do quite a lot of live streams these days, both to YouTube and Facebook. And so I'm just trying to bring up my Facebook one. Where are we? My computer's decided to... There we go. So I've got a Facebook page, Smart Energy Labs, with an S on the end. So facebook.com/Smart Energy Labs. And I give a lot of live talks. I'm doing every Sunday, which unfortunately, because of your 14-hour time difference, will be about midnight on Saturday. So if you're really partying hard and you just want to look at something educational on Facebook at midnight, I'll be there. And it's an interactive session. So it's I call it Toolbox Tech Talk, where people ask me questions and I answer them live. But it's also available after that. So, if you don't want to stay up to midnight, you can always check it out the next day. So every Sunday in Australia, but every midnight Saturday in Chile, there'll be me popping up there, chatting away to you. Okay, well, back to you, David. So any last questions?
That seems like a great idea for our next Sunday, I think. I myself, I wanted to ask you about, we talked especially about residential system. Are there any important difference to commercial use of grid parallel batteries?
Yes, there's a big difference. Well, certainly in Australia, we have peak demand tariffs. So if a customer goes over a certain amount of demand for a certain period of time, so within a 30-minute window typically, if they say draw more than 100 amps, they might be charged a whole lot more for their electricity for the rest of the billing period. So it could be for the rest of the month, they pay a higher rate. So it's like a penalty for being a peaky energy user. But by putting a relatively small battery system in there, you can trim those peaks off so they don't happen without having to run around and turn off equipment in the factory. So yeah, batteries can be very useful for peak demand lopping. For backup purposes, maybe only for IT services, etc. It's not really a big one. So yeah, batteries aren't a strong market for commercial unless they have that peak demand tariff problem.
Okay. The other question I wanted to ask you, last time you shared with us the names actually of the technical norms you use in Australia. I don't know if you could again share this one in the presentation. I don't know, the PDF you will send us after that, it would be, or you can just write it down. I don't know if you don't know them by heart.
You mean the standards?
The standard, right? Thank you very much.
Yep. Actually, I'll write them down. But while I'm writing them down, I just realised there is another case for solar and batteries for commercial, and it actually just came to me yesterday as a design consultation. This person has a large hydroponic farm. They consume about 240 kilowatts continuously, so they're a big energy user. The utility came to them and said, we will pay you an enormous amount of money if you don't consume power from 11 o'clock till 1 o'clock. So for 2 hours, if you stop consuming, we'll pay you. So the incentive is so strong that they want to put in, it's about 3/4 of a megawatt system. That's not going to be cheap to be able to turn off their hydroponic farm for 2 hours a day. So there's another incentive, which is where the utility can see that reducing demand is cheaper than increasing capacity on their grid.
Okay.
Yeah, and it's often done at a very focused level. It might be just this feeder is the problem feeder. We could spend $10 million upgrading that feeder, or we could pay the customer to turn off.
Okay, great.
Now, the standards I'm going to write here is for PV, for inverters paralleling with the grid, and for battery systems on or off grid. So I'll just bring it up on my camera here. Here we go. So
Okay.
here you go.
Yeah.
So
So
that's
everybody just take a picture right now.
now you can actually buy these standards straight off Standards Australia website. So.
And just to close my question I made about commercial batteries, you talked about the energy aggregator that basically joins several or a lot of residential battery systems in order to make services to the grid. Do they also include commercial batteries, or is it, or in Australia it's basically with residential system?
At the moment, it's just residential, and it's a very small market because of the rules of the electricity market.
Okay.
You can't just at an individual level sell your power. You have to sell it through a retailer, and the retailer has to aggregate those customers. But there is a rule change coming, which will probably make it easier.
Okay, then we have a question. Thank you very much. We have a question from Santiago, who's asking the best question you always can do when you're talking about some products. Which batteries could you recommend for these kind of systems?
Oh, that's an easy one to answer, but I'll answer in 10 years' time.
Very good.
I'm not being facetious. The problem is that products keep coming out. So I've got this lab here, the Smart Energy Lab, and almost every week a new system arrives for me to test and trial, and it ends up being part of my training system here. And it always is the latest, greatest thing that the marketing. This is a beautiful battery. It's made of super high quality materials, etc. But you can't tell from the marketing. You actually put it to use and find out. And cycling a battery takes a long, long time. You can't really accelerate the cycle. So when it says it's rated for, I've got one battery here. It's rated for 22,000 cycles. Now, I won't live long enough to cycle it.
Okay, then you have to tell us again.
Yeah, that's right.
Okay, I think I have a last question. It's quite long from Christian. He seems to have a lot of questions about energy batteries. Sistemas all in. Habla he's talking about the system the hybrid inverter, which includes actually, I think, both direction. Christian, it's too long your question. I cannot. I need like half an hour to translate it.
I think he's referring to this one. Is that correct? It has both a grid side and a load side.
Yes, and he's asking, con su salida backup es capaz de soportar la carga de consumo posible utiliza un ATS entre la salida y backup. He wants to use an automatic transfer switch between the backup output of the inverter and the grid in order to put energy to a load complete. I don't know. It's too long. I don't know if you got me.
That it is quite possible to do this.
Yes, so I think that's the thing he wants to.
Yep. Yeah, so I have exactly this system on my microgrid. So I've got a 250 amp transfer switch here because I've got we're in the process of installing a 70 kilowatt solar farm that's going to be connected, and it needs the pass-through capability of this is only 63 amps. So we can't use the internal ATS. It's not powerful enough. In fact, this inverter is 6 inverters. There's actually 6 of them all working in parallel. So we've got an external ATS, and this is just controlled by directly from the inverter. So it does the transfer. The inverter goes, I'll switch to grid or not whenever because of different conditions. So yeah, you can do it.
Okay, great. So Christian, you can do it, and please try to do questions that are a little bit shorter than that. Okay, it seems we do not have any more questions. No, it's not. So again, Glenn, it seems it was our last, or for at least for August, it was our last meeting here, Australia, Chile. Again, I really appreciate your time and your great presentations. Everybody loves you here in Chile. You're like famous, so be careful when you come visiting Chile one day. You need sunglasses. We really appreciate it. It was very interesting for us. As I already said to you, we are just working on the standards in Chile for battery use and parallel battery use. And clearly we will have some questions again in the future. I hope we will stay in contact. And well, thanks again.
Thank you. It's been my pleasure. Hope to see
Okay.
you on my my Facebook Live sometime.
Yeah, sure. We will check that next Sunday.
It's Saturday night, remember? Midnight.
Ah, sorry. Yeah, right. You're right. Okay, just in Spanish. Bueno, muchas gracias a todos. Eso en general era la última parte planificada con Glenn. Como dijo la Marcela ya, tenemos todas las grabaciones también en YouTube, probablemente también por otro lado. Por favor, háganse socios de ACESOL. Necesitamos juntar muchos socios porque al final eso hace la fuerza de una asociación para que también sigamos informándonos y sigamos con estas charlas interesantes. Así que gracias a todos, que tengan una buena tarde y nos vemos pronto.
Gracias, Glenn.
Thank you, Glenn.
Thank you so much.
See you, Marcella. See you, David. See you, everyone.
See you soon. Thank you. Bye-bye.